be talking about wrapping up the discussion on space curvilinear motion. Space curvilinear motion, and then we want to introduce the concept of relative motion. And I think the one useful thing would be to help you a little bit with a problem that's in your homework. And if you look in your book, page 87, problem 178 is assigned. And since this problem didn't have the answers provided, I've written them down here so you can write them down. So your goal is to obtain those components. And then I want to give you a clue that'll help you in the solution there.
Can you zoom in on them a little?
Oh yeah, what's that?
Okay.
92.
Yeah, I'll zoom in a little more.
Thank you.
Reset that a bit. Is that all right?
Mm-hmm.
Okay. Now, here's your reference point over here, and you can see the defined axes for x, y, and x rotated into y gives you z. So it's a right-handed coordinate system. And notice that this tracking, since the aircraft is taken off and it's tracking along the YZ plane and rising at a rate of 1 to 2, and a slope of 1 to 2 there, and ascending with a certain speed, what we want to do is come up with these components, and you notice what they were asking you to find is phi dot, theta dot, and the capital R component of velocity. Here's what's going to help you. Since the tracking device over here, the radar, is locked onto the aircraft, you can see that the tracking device is rotating to the right, shown here as theta dot. Is theta dot positive or negative? Based on the derivation of coordinates we looked at the other day.
It's going clockwise.
Clockwise is negative.
It's negative because the way that we defined positive theta was sweeping from x towards y. So as that angle theta would open up, that would be the sense of positive theta rotation, which is counter to what you see prescribed here, trying to track that aircraft which is rising to our right. Okay, with that in mind then, theta dot is negative. And then also, here's a key to being able to work this out. You need to decompose the plane speed v into a component that is in the y direction, v sub y here. Okay? So you have to get that component. That component, that v sub y component, is going to contribute to what term in your spherical coordinate system for your velocity. That's going to play a part in which part? In the rotational part of this tracking device. Right? The rotational part of that tracking device. So you don't use the entire V. You have to use that Vy component. Because that's what's causing this capital R vector to rotate to your right. Now, what's causing the capital R to lengthen? The capital R to lengthen. Here's distance capital R. And keep in mind you have a unit vector that's pointing radially outward along capital R. What component of velocity is contributing to that lengthening?
Just up.
It's
not heading toward or away.
Right, it's the Z component that is directed upward. And there's a part of that Z component that's upward that is outward in the direction of capital R. So a portion of VZ is going to be outward along capital R. Now what's going to contribute to the change in phi to yield this answer for phi dot? what's going to contribute to the calculation for phi dot? What part of the velocity?
V sub big R, that one.
V
Vz, the component of Vz that is now pointing upward and perpendicular to this R. So it's actually, it's hard to see it here. I don't have a pencil on me. I don't want to use ink on the book. But it's going to be pointing up. It's the portion of the Vz here that is going to be pointing upward and perpendicular to this capital R. So you're going to decompose, in other words, Vz into two parts. One part that is pointing in the direction of capital R hat, and the other portion that's pointing perpendicular to capital R and up and to our left here. In other words, you're going to have the sine, you're going to have a, notice here, Vy is going to be V times the cosine of that interior angle to get that horizontal component, and then you'll be using it to capture what theta dot is. The Vz would then be involved with using the complementary angle to phi to decompose it.
Why wouldn't VZ be V sub big R?
It's not just in the, let me see if I can draw this on the board a little bit for you. If we would look in sideways on this, if we'd look in sideways where we see phi here, we have a Vz component here. What I'm getting at is you've got to decompose, this is your capital R hat vector. So you got to decompose Vz into this component, and the other component is pointing this way.
Okay, I see.
Okay? So there's your V sub capital R term, and here is your V sub phi term.
I see.
Okay. You have to draw usually additional sketches to be able to handle these three-dimensional kind of problems. Additional small little two-dimensional sketches frequently. Okay? Are you struggling with any of the prior homework? Normal, tangential, or polar? Probably have time to spend a few minutes on that.
Number 163. We found the radius. Theta dot's given. We know theta double dot.
See if I can get that up here so people can have a reference.
But going from there, I'm not certain. I think we probably, if we could find the total velocity of the object, we'd be good to go. But finding that is, I think, where we're getting stuck.
Okay. So what we have here is we have a slug that's inside this tube, hooked, and the slug is hooked to a cord that's fixed down here at D. And then what happens is this arm here with the tube is rotating upward, and it's pulling the slug up through the tube, right? Okay. And these problems are in the section associated, we could handle it a couple different ways. This is in the section on normal tangential still.
This is polar.
Oh, this is the polar section, okay. Here's the slug on that rod at some angle theta, at some distance r from the pole. And the rate, theta dot, is given to us as 4 radians per second. Keep in mind that pi is half a rotation. Pi is half a rotation. So it's a little more than half a revolution per second. So you kind of have a physical sense then of how fast this arm is rotating. So it's always good to sort of think about those things, get a physical sense for it. Okay. They also tell us that the length of chord is equal to R, capital R, and capital R is the length of this chamber. And this thing begins down here when theta equals 0. Little r is equal to 0 when theta is equal to 0. Determine the magnitude A of the acceleration of the slider when you're at 30 degrees. So we want the magnitude when theta equals 30 degrees. Okay. How many of you have done this problem already?
I've worked on it.
A couple of you have worked on it as all? Okay. So this is what we're looking for. Let's go ahead and play with it a little bit. If this is in circular motion, then we have pulled this chord length right here. We've pulled that much of the overall chord length out of the cylinder. And that distance being pulled out is going to be equal to the little r, is it not?
Yeah, it will be.
Equal to the little r? Because the cord is hooked onto the slug, and it goes up here and then out and down to its fixed point down over here. So we pulled little r out of there, which means that little r is equal to, well, can we write a description of that? I guess we have a chord length right here. This is capital R.
That's capital.
This is capital R. This is theta.
So you can use law of sines on it.
Right. Or the fact that it's an isosceles triangle, we can see that that piece, if we imagine bisecting this angle, we could work up or we could use law. Well, we have side angle side here, don't we? Actually, let's go ahead and do that. We have a side angle side condition from trig. And when the emphasis is on the side length, you use which law? Law of sines or law of cosines?
Law of sines.
Law of cosines, if the emphasis is on the sides. We don't know this length, and this happens to be our little r, doesn't it? Okay, that little length is little r. So if we set this up, let's go ahead and do it. We write the law of cosines on this, so little r squared is equal to capital R squared plus capital R squared minus 2 times these other two side lengths times the cosine of the angle that happens to be opposite this side that we're interested in, which happens to be this angle theta. I'm going to get a better marker. Okay. So what we end up here is, you can see there's a common r squared. So when we find r, we can pull that r out of this, the capital R out of the square root, and we're left with, this is 2r squared minus 2r squared cosine theta. So if we pull out the r squared, we're left with, let's go ahead and pull a root 2 out of there as well. Radical of 2r pulled out, and you're left with 1 minus cosine theta inside. So there's r as a function of theta. So when we're at 30 degrees, we could determine that value. However, r changes with time, doesn't it? R changes with time. So let's go back and examine theta for a second. We know that theta dot was given to us as 4 radians per second. So therefore, theta is going to be equal to what in terms of time? 4t radians. 4t radians. Feel good? Okay, so we've got that. We could write then r as a function of time by making that substitution. Now I'm wondering what the best approach is going to be. Radical 2r square root of 1 minus cosine of 4t. Now what's our objective? Magnitude of the acceleration. Now the magnitude of the acceleration, we know, this is where we're heading. So what you always want to do is to sort of have some idea of what path you might want to take. So here's our magnitude of the acceleration, and so inside this radical then we have our radial acceleration term, which is r double dot minus r theta dot squared. And we have our theta directed component, which is r theta double dot plus 2r dot theta dot. Squared. These are all time-dependent relationships, and we have a description for theta, theta dot, and theta double dot being 0. Right? So we have here also that theta double dot is equal to 0 because of the constant rotational rate. And we have a description of r over here in terms of time. Is this object, as this arm sweeps up, is it speeding up or slowing down, the slug in the tube?
Speeding up.
Initially it's down here, right? And so is there much of this length of cord being pulled out right away initially?
No.
No, not much. And as it gets up here further, isn't there, for a small rotation here, isn't there a more proportional length of cord being pulled? Okay? You see that? You have a sense of that? Okay, so it appears that that's going to be the case. Now, you can always fall back on the mathematics, but you also can try to conjecture about what you think the physical motion is going to be. Okay, and see if it all fits together. Okay. So what we do know then is down here this theta double dot term is going to go to 0 on us. And I think we could just crank derivatives on the rest of that and work it on out. Can I let you folks take it from there? Okay. And the key was probably working up this relationship over here.
I tried that, but I used law of sines instead, and it came out pretty nasty. So
Okay.
that came out a lot better.
Now,
A lot more straightforward.
what did you use, how did you use law of sines?
Well, I solved for the two base angles there. Or
This
opposite.
angle and that one?
Yeah,
Yeah. So
As-
let's call that, say, angle phi.
yeah.
And
that
so
would
you
be-
could do that,
Mhm.
but at 30 degrees, but the thing is, this is a time-dependent function
Yeah, so you end up with another time-dependent function
for phi.
of those two angles.
That's
yeah.
correct. So phi, see, twice phi plus theta has to be pi,
Mhm.
right? Okay, so therefore phi is going to be pi minus theta over 2. and then using law of sines on it. And law of sines, remember, always pairs up an angle with its opposite side. And then another piece of information, another pairing, okay, to be able to use law of sines. And so that's why I would definitely avoid that because like you said, you got the mathematics started to get a little screwy. If you work your way around the given information on an oblique triangle, work your way around, side, angle, side known, you can identify which law you should probably use on it. Okay. Does everybody remember the law on how you do it? How you do it? I did it here for the specific example. Anybody not? Everybody remembers it. The way I teach it in trig is I say, well, you all remember the Pythagorean Theorem, right? And so just for the heck of it, I'm going to change the letters around from the way you usually see it. You know it's a Pythagorean relationship looking something like that. But the fact that you don't have a right triangle, you've made the triangle oblique, you have to compensate for that, you know, without going through the proof. And what you do is you subtract off twice this leg times that leg times the cosine of the angle opposite this side over here. So that's an easy way for you to remember the law of cosines. Okay. I'd rather go ahead and move on to some other material. I'm going to let you guys finish this problem out. Find your R dot carefully, R double dot, drop them in here. It should tidy up pretty nicely.